Okay, welcome to week 2, part 1 of R for Data Science. This week we're going to take a look at some of the fundamentals of R programming. R is a prerequisite for this course, of course, but my own experience learning S, the predecessor of R, and later R, back in the good old days, was that it was possible to do an awful lot of stuff with R, manipulating an awful lot of data, without really having a very clear idea of what was going on. You would hack away on things until you got something to work, and you would thank your lucky stars and go on to the next problem. In any case, we're going to build up some basics of R here this week to make sure that everybody is clear on dealing with data up to and including data frame objects. Okay. Now, one thing I do want to say is that the history of R is very long. R dates back, as I said, to a predecessor language called S that was developed at Bell Labs quite a long time ago. And over the years, R has developed many different quirky ways of doing certain things. You'll often discover that there are multiple different ways of doing the same thing. I'm not going to go through a catalog of all the various different ways that you can do certain things. So we're going to just, march ahead so that you have a way of dealing with numbers and integers and strings and vectors and lists and data frames and so on. Okay, so when we have our R environment running, and I'm going to be using what is this thing? Oh, RStudio. I'm going to be using RStudio for these examples. At the greater than symbol prompt, you can type R code. And in this first example, I'm going to create a variable named A, to which I'm assigning the numeric value 123. Okay, so A is a variable name, and A is associated with an object, and that object contains the value 123. Now, one of the very nice things about RStudio is that it shows you each time a variable is created and what the variable's current value is. If I type the name of an object, if I type the variable name at the prompt, I will be shown what the current representation or value of that object is. And then I can quit from R by using the Q function. I'm actually not going to do that. I'm going to stay in R. And of course, if you're using a graphical user interface like this, you can also go up to File, Quit Session, or just hit the X in the upper right corner, or what have you. Now, this symbol, although it's a pair of characters, the less than symbol and the dash, is the preferred way of doing an assignment in R. And I'm going to call that the gets operation. So I'm going to say A gets 123. Now, you need to know what the rules are for what you can legally name your variables. The first character in a variable name has to be a letter or a period. Upper and lowercase letters in R are distinct, just like they are in most modern programming languages. So if I create this variable capital A, which gets a 3, that's an entirely different object, entirely different variable name from the lowercase a that I created before. And in fact, up in the values in the upper right corner here, I can see that they're separate. Now, following that first character, you can have more characters if you wish. And those characters can be upper or lowercase letters. They can be period characters. They can be digit characters between 0 and 9, or they can be underscores. Okay? Now, one restriction on that is that although the first character is allowed to be a period, if the first character is a period, the next character cannot be a digit because, for example, 0.9 is the floating point value, 0.9. All right? But I can use a dot as the first character in a variable name. I am, for many of you, this won't mean anything, I suppose. But I am a sad Minnesota Vikings fan, and most recently, the Vikings were beaten on the way to the Super Bowl by the New Orleans Saints, who have a sort of a motto, "Who dat?" So this is in honor of the vicious Saints that knocked off my Vikings. So I have a variable here, .who.dat, which I'm assigning the string Saints to. And in R, a string is contained between double quotes. Okay? A Boolean value of true has to be typed as true in all uppercase, false is false in all uppercase. There is also a not available Boolean value, but we'll leave that for later. This variable name is illegal. It would be legal in several other languages that you may be familiar with, but you're not allowed in R to type a variable name whose name starts with an underscore. Okay, now you can see what variables currently exist. You can list the objects, if you will. Of course, in RStudio, you can just look at the upper right corner to see what variables you have. Although a variable whose name starts with a dot, like whodat, well, .who.dat, is hidden from view by default. So the ls command, this is borrowed from the Unix ls command. This lists the names of your objects. Or I can use the objects function also to list the names of my objects. Now, this business of hiding variable names whose names start with dot is another thing that's borrowed from the Unix operating system, and of course its successor, the Linux operating system, which by default hides files whose names start with a dot from the ls command that lists file names. In Unix, if I want to see all the file names, if I'm pretending that this is a shell prompt rather than an R prompt, I would say ls-a to see all of the files. If I want to do the similar thing in R, I can say, it's a little clunkier, I can say, you can see that my help message says all.names equals true, and that will show me my .who.dat variable. I'll also discover that I have a random seed variable that I didn't know about, and in fact, this is why this is why variables whose names start with a dot are hidden from view, so that they can be used by packages developed by others for internal details that typically you should not mess with. So I don't want to mess with the random seed used by various random number generation functions within R. All right. Well, in any case, I suppose that's an example of the kind of historical stuff I wasn't planning to get into. Anyway, moving on. In terms of low-level data types that we can store values into, or that we can represent values as, we're going to use numeric, integer, character, and logical data types. R also provides complex numbers and raw data, but we're not going to use any of that for the kind of work that we need to do. Now, numeric data in R is represented in a 64-bit double precision floating point notation. If you are familiar with other languages like Java or C or C++, you'll recognize this double data type. Integer values in R are stored in 32-bit integer representations, which means they correspond to the long int data type in Java or C++. Character is how character strings are designated, and the logical data type has values true and false, and also not available, which we'll get to a little bit later. Okay, so I have my variable a that I created, and I can ask what the type of that thing is by using the typeof function. This will tell me the low-level data type of the object that a is the name for. And indeed, I'm told that that thing is double. Now, if I want to create an int value with a variable naming it, here I'm saying b gets 123L. So L here is actually, in the C language, how you would represent a long integer constant. That's why in R, L is used to represent integer values as opposed to floating point values. So B is 123, and in my course notes I see that I got carried away and put the L there, but actually the L is not displayed, which is sort of annoying. However, if I ask for the type of B, I do get told that that is an integer value rather than a floating point value. Here's an example of a string in double quotes. So the C variable is now this string in double quotes, and type of C will tell me that that thing is of character data type. And then finally, for the fourth of these low-level data types we're going to use, here's an example of a Boolean, or sorry, generically Boolean, capital B Boolean after bool, but in R these are referred to as logical values. Okay, so those are the four low-level data types that we will need to care about. We're going to need to do arithmetic, obviously, and R has familiar arithmetic operators that you're probably used to from other languages as well. It does provide exponentiation using the caret or up arrow or circumflex or whatever you prefer to call that character. I like to call it the caret, C-A-R-E-T, as opposed to the vegetable. And it does the obvious thing, so 2 squared is 4. Now, the plus and minus symbols can be used either in a unary form or a binary form. In unary form, they just indicate whether a value is positive or negative. In real life, you'll never see anybody use the unary plus sign, other than to tell you that you can in a class like this. The modulus operator is the double parenthesis, the double, and not parenthesis, the double percent sign symbol. Okay. So if I were to ask for 12 mod 5, that gives me a 2, because the remainder after division by 5 is a 2. It's important to note, if you don't have this memorized, that the modulus operator in R is higher precedence than the binary multiplication and division. In most languages, those are the same precedence. So this, I suppose, in the rare instance where you actually use the modulus for something, this could trip you up. And then the lowest precedence of these arithmetic operators are the binary addition and subtraction. Okay, so this table shows you from high precedence down to low precedence, And each of the operators that's on the same line has the same precedence as each other. All right, so unary plus and unary minus have the same precedence as each other. Multiplication and division have the same precedence as each other. And addition and subtraction have the same precedence as each other. You can, of course, use the parentheses for overriding these precedence rules, or the associativity rules, or just for making things more clear to yourself or other people. Almost all of the binary arithmetic operators associate from left to right. All right, so if you type something like 1 plus 2 plus 3, that's going to be evaluated as 1 plus 2 plus 3. And if you say 1 divided by 5 times 2, this is going to be evaluated as 1 divided by 5, that quantity times 2. So that's going to give me a 0.4 as opposed to a 0.1, let's say. Now, the one exception to this associativity rule is exponentiation. Exponentiation associates from right to left instead of left to right. So if I say 2 caret 3 caret 2, if you weren't aware of the association rules, you might glance at that and think, oh, okay, so 2 cubed is 8, 8 squared is 64. Ah, rats. No, because this is evaluated from right to left. So what we actually have here is 3 squared, which is 9, and then 2 to the 9th power, which is 512. Similarly, since the modulus operator has higher precedence than multiplication, if I compute 3 times 5 mod 3, this is not computing 15 mod 3, which is 0. Instead, what it's computing is 3 times 5 mod 3. 5 mod 3 is 2, and 3 times 2 is going to give me a 6. All right, so regrettably, these precedence and associativity rules of arithmetic operators is something that you really ought to know. You really ought to. This is one of these irritating things, you know, like the cornerstone of a solid building that you really ought to have memorized. Now, because integer values are represented in a 32-bit representation, the range of values that you can put into an integer is from minus to 147,438,647 up to positive of that same value. And if you try to go outside that range, you'll get yelled at. So if I were to say J gets to 147,483,647L, I have to remember to use the L, otherwise it's going to be treated as a floating point number. All right, this works fine. And the type of J is integer. But if I try to go one beyond that, if I try to go up to 8, I will get a warning saying, no, that's too big to fit. And consequently, the value is going to be treated as numeric. And by numeric, what is meant here is double. So J is now actually a double, even though I attempted to create it as an integer. All right, so be aware of that. The numeric types, since they have to fit into a 64-bit double precision representation, have magnitudes ranging between roughly 10 to the plus or minus 308th power. And you also need to be aware that you only have 15 or 16 digits of precision with double precision values as well. All right, I actually showed you this first part here of the integers, but let's take a look at these ranges and precisions of floating point values. If I say x gets 1e308. Okay, so 1e308 is how you write a literal value of 1 times 10 to the 308th power as a floating point number. I don't get yelled at, which is nice. And when I display it, I get 1e plus 308. And if I ask for the type of that thing, I get told, yes, that's a double. But if I try to go to the next higher power of 10, well, I didn't get yelled at, but R realized that that was too big to fit, and so it uses the special value inf to represent a conceptually infinite value that's too large to be represented in the machine. Now, the type of x is still going to be double, but it's pinned at positive infinity here. And if I say x divided by 100, trying to pull that back down below the level of infinity, well, it doesn't work. Once it's pinned at infinity, infinity operated on by anything is just going to be infinity. Okay, so beware of values that are too big to represent or too small to represent. If you go in the small direction, you end up getting a 0. So x gets, come on, 10 to the minus 308. Whoop, 308 works fine. That's just a tiny value. But if I try to go too far in the negative magnitude direction, that still worked. Okay, I forget exactly what the limit there is, that below which you can't go. So let me just say, 400. Okay, at a certain point, as your magnitude gets too small, it just gets chopped off to 0, and then you're stuck at 0. So if you try to say x times 1,000, it's still 0. Okie doke. So as far as base data types, we have integers, we have numeric, which is double precision or double on these systems. We have character, which is R speak for strings, and we have logical. However, in reality, in R, there's no such thing as a scalar data type. All values in R are stored in some kind of data structure, and the simplest kind of data structure in R that's built into the language is the vector. The items that are stored within a vector all have to be of the same data type as each other. You can also have lists, which have elements that are not necessarily of the same data type. You can have a matrix, which is a two-dimensional thing, rows and columns, which, similarly to a vector, all of the objects in a matrix have to be the same data type. And then our eventual goal here is to make sure that we know what we need to know about data frames. A data frame is essentially like a list of lists, where each list you can think of as a column, and each list in this list of lists you can think of as a column, and all of the lists in the list of lists have to have the same number of values in them, and we can think of the length of each one of those things as the number of rows that the data frame contains. So when we say something like m gets 12 and display m, you'll notice that there's this 1 in square brackets in front of the 12. M is not actually a scalar value. M is instead a vector of length 1. And in fact, we can use the length function to see that. All right, so the length of m is 1, and m is actually a vector. To create vectors of more than one item, there are a variety of tools that we can use. For example, the C function, C is short for combine, will combine together a sequence of values. You separate the values with commas. All right, so here we've got 1, 2, 1, 3, 1, 4 in parentheses for the function, and C combines those 6 values together into a vector of 6 items. Now, when I display V1, you'll notice that it still has a 1 in square brackets in front. That's just to indicate to you that that is the first item in the vector V1 to the right of the 1 in square brackets. We'll only see that number changing to something else when the vector gets to be quite long. So I'll show you that basically when the vector gets so long that it won't fit in a single line on the screen any longer. All right, so when I ask for type of V1, even though these look like integers, of course, they're actually numeric or double values because I did not use the L to force them to be integers. In this next example, I'm also using the C combine function, but this time I want to make sure that each of these values is treated as an int, an integer value. Too many languages in my head here. Okay, so V2 looks the same in the output. You may or may not find this frustrating, that the output, you can't really tell the difference between floating point and integer values, but type of will clear up for me that V2 is a vector of integer values rather than double precision floating point values. Now, other ways of creating a vector are to use the colon notation to define a sequence. If I just say 1:5, that creates a, in this case, unnamed vector of sequential integers between 1 and 5 inclusive. And here I can show you what I'm talking about that square bracket 1. If I say 1:50, there's not room on this line of output in my RStudio terminal to see 50 values on a single line. And so they're going to wrap around, and I get shown, okay, the first item in the vector started here, it's the 1. The 19th item in the vector is at the beginning of the next line, and it's 19. And the 37th item in the vector is here on the next line down. Now, it's maybe a little unfortunate that because of the sequence that I chose, those numbers match the numbers that are being displayed. You can have any beginning and ending value that you wish for your sequence. So let me try something like 50:100. And here we see that the first value is 50, the 15th value is 64, the 29th value is 78, and so forth. Okay, so that's what those square bracketed numbers are about. The thing being displayed is a vector, and the numbers are indicating what the index is of the first item in each line of output being displayed. Okay, so on slide 17, we're saying V3 gets this sequence of values. So V3 is now a vector and containing integers. Interesting. So I have a typo here in my slide. That should be integers rather than double. Right here. Okay. So this colon notation lets me have sequential integers. There's also a function named seq, S-E-Q, that allows me to create sequences with more flexibility. If I say v4 gets seek 5, the seek function assumes that that's the last value that I want to have in my sequence, and that the first value by default is going to be a 1. So this gives me the same result as using 1:5 to create the value for v4. But if I say sequence and give 2 arguments, 5, 10, let's say, in this case, the first value is taken as the starting value, and the second value is the ending value, so I'm going to get all of the values between 5 and 10. All right, 5, 6, 7, 8, 9, 10. If I put a third value in, that is taken as the step-by size. All right, so if I ask for a sequence from 5 up to 10, but with a step size of 2, then I'm going to get only every other value between 5 and 10, and 10 itself will not be included. So I get 5, 7, 9. The next value that would be displayed that would be formed into the vector would be 11, but that's beyond 10, so we stop. Now, seek is able to count downwards as well as upwards. So if I put these values the other way around, 10, 5, seek is smart enough to figure out, oh, okay, well, 10 is greater than 5, so let me count downwards from 10 to 5. In this case, if I try to give a size of 2, thinking that I'm going to get 10, 8, 6, for example, the step-by has to be added to each value to move on to the next one. In this case, I would go from 10 to 12, and that's an error. So seek yells at me, and in fact tells me exactly what I've done wrong. I've got the wrong sign in the by argument. So the by argument is this third one. Let me try seek 10, 5, 5, -2. And then I'll get what I want. All right, 10, 8, 6. Now, these arguments do have names. By is the name of the third argument. So I can say seek from gets 10, to gets 20, by equals 2, to be a little more explicit to somebody reading my code about what I'm using these various arguments for. Okay? So that's just, that can all be abbreviated, as I've shown, by just saying 10, 20, 2. If you don't specify the argument names, the parameter names, then by their position, the seek function will assume that they are in order from to by. Unless, of course, you only give one argument. If I say seek 5, that's equivalent to saying seek 2 gets 5, and from is assumed to be 1. Alrighty. Within a vector, I can access or subscript the nth item by using the square bracket notation with n as my subscript. And unlike a lot of other languages that you may be acquainted with, well, of course, you're supposed to be acquainted with R here, but R counts its subscripts starting from 1 rather than from 0, as Java and C++ and C and everybody else, Python does, and so on. So if I have v4 here with these values 1, 2, 3, 4, 5, actually that's a bad example. Let me look at v1. Right, this one's a little more interesting because the values and the indexes for the values are not necessarily exactly the same. So if I say v1 sub 3, v1 sub 3 is going to be this third item in the vector v1. v1 sub 4 is going to be the fourth item, so it will be this value 3. And notice that, again, R does not really have such a thing as a scalar, so what I'm really getting here is one character subvectors out of this vector v1. I can modify the value within a vector by using my gets operator. Oh, interesting. Okay, well, I do too much Python and C++ programming, so I accidentally used an equal sign there, as I almost did live. Now, the equal sign will work in almost all cases, but I want to be consistent with correct practice here. All right, so I don't actually have a vector named v, so that was an error. But when I say v1 sub 4 gets a minus 7, that did modify what had been this value 3 in v1 to be a minus 7 instead. Okay, now rather than using individual subscripts, you can actually use a vector of subscripts to get a subvector out of the vector. All right, here is a, well, I've just displayed v1, so it's 1, 2, 1, minus 7, 1, 4. If I ask for the subvector starting from item sub 2 up to and including item sub 4, that's going to give me these three values as a vector, 2, 1, and minus 7. It's perfectly fine to change the subscript order to go from high indexes down to low indexes. Here I'm using the combine function 642 to create my index vector. This is going to give me the sub 6 item followed by the sub 4 item and then the sub 2 item as a vector. Panicked for a moment there. I had just mistyped the name of the variable. v1, not vi. Okay, there we go. Okay, so v1 sub c642 gives me the three items that I claimed. It's also okay to ask for a particular subscript multiple times, and that's no problem. So if I say v1 sub combined together 6666, that's going to give me a vector of item sub 6 from v1 repeated 4 times. All right, so I have a vector of 4 items, and each of those items is just a copy of the last item contained within the vector v1. It's also possible to use a logical vector to indicate which values you would like to pluck out. Here is a logical vector. Let me create a separate name for this. I'm going to call it vlog, although it's not a vlog in the usual sense. So vlog is going to be true, true, false, 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 true. Whoops, forgot my gets. Okay, so vlog, vector of logicals, is 6 wide. I've got 6 values in v1. So vlog, I want to have 6 logical values. Type of vector of logicals is logical, right? And if I now use vlog as a subscript into v1, what will happen is that each value where the index is true is going to be plucked out in my returned or yielded subvector, and the false ones will not be selected. So I have true, true, false, 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 true. Consequently, what I should get out from this is a vector 1, 2, 4. And that is indeed what I get. Now, the C function I have been using for combining together what casually appear to be scalars to create a vector. But remember that the quote scalars unquote themselves are not really scalars. They are actually one-item vectors. So I can use the C function to combine together vectors of arbitrary length. Here is my v1 vector. Here is the v2 vector that I created some while ago. And if I create a new vector v5 by combining v1, 8, v2, all right, I'm not doing anything strange here. I am combining the vector v1 with the vector 8 and the vector v2 to get a single vector consisting of the values copied from v1 followed by an 8 followed by the values copied from v2. All right? So, whoops. Hey. All right, so the length of v5 is better be 10. Yeah. Okay, so I had 6 values copied in from v1, 3 values from v2, and then the vector 8, the vector with one item 8 that I put in between. You can do arithmetic with vectors, and it's not surprising how this works. Here's my v2, 1, 3, 5. If I say v2 times 3, now technically what I'm doing here is multiplying a vector times a vector. But it's treated as, I can think of it almost as being a scalar here, and my result is going to be 3, 9, 15. I'm actually going to store that into, and once again, I see that I mistakenly used the single equal sign, which will work in cases like this. 2 times 3. All right, so v6 is going to get the vector resulting from multiplying the vector v2 times the vector 3. And that's the 3, 9, 15. Now, in fact, what's happening when I say v2 times 3 is that R notices that the lengths of these two vectors are not the same. That is, the length of v2 is 1. The length of 3, pardon me, I said that backwards. The length of v2 is 3. The length of 3 is 1. And so what R does automatically is to pretend as though that 3 was a vector that's also of the same length as v2. And then what's really happening here is a pairwise multiplication of the first item from v2 with the first item from this vector of 3 3's, and then the second item from v2 with the second item from the vector of 3 3's, and so on. So that gives me the same result. And in fact, all right, so v2 is 1, 3, 5, and v6 is 3, 9, 15. So if I say v2 times v6, once again, this produces a vector of 3 items in which the pairs of values are multiplied. So 1 times 3 gives me a 3, 3 times 9 gives me a 27, and 5 times 15 gives me a 75. All right, and so that's the result that I get from that multiplication. Okay, well, that is it for part 1. I will continue with a little more about vectors, and we'll move into talking about lists and matrices and data frames, and that will be the second half of this week's lecture material.